So the very first thing is what we are going to have is geometrical interpretation of definite integral. So when you are talking about some integration a to b f of x dx, okay, how we can relate it with the geometry is in terms of area under the curve. Okay, but it's not always be like area under the curve. So for means like it depends on the curve equation. Okay, so suppose f of x is positive. Okay, so slice above the x-axis. So it is between a and this is b. Okay, so integration a to b f of x dx will give you the area between this covered by under the curve. This is your f of x on the interval a to b. How it is going to be that that is the answer given by the Riemann here. Okay, so that we are going to look at as well. Okay, right. So that's very okay. So let's have here. So a function y be positive, defined on a closed interval ab. Then find the area A of the region bounded by the curve y equals to f of x and vertical lines x equals to a and x equals to b and the x-axis. So as told, so this is the curve here, blue line is the curve y equals to f of x. The vertical lines are the lines parallel to the y-axis. Okay, so the area bounded by these and x-axis, okay, is given by this here. And we want to approximate the area of this part here. Okay, so again the computer will not understand what is integration a to b. Okay, so it certainly require approximation. Okay, and many functions are there like you have this is e to the power minus x square dx that you cannot integrate. So what you need alternatively, you need to at least should have some approximation. So approximation means you need to go for the better approximation, means how much good you require, means it depends on the how much error you allow in the integration. Okay, so desired accuracy will take place and then error analysis will take place and so on. So how to get this approximation we are going to try to understand now. Okay, so the simplest way of approximating the area is this area subdivide in the finite number of rectangles. If you means like you draw the vertical lines here, you draw the vertical lines means suppose they are 5 or 6 or 7 somewhere, so you can name them like let's say this is A and this is like A1 and this is B1, and these are the points like x1, x2, x3, let's say x4, let's say x5. Now you want to approximate the area by using the rectangle. So there are many ways. There are many ways to approximate this. Only I have considered in between x1, x2, so 5 points. Okay, so you may increase this number of points as well. So this one is I will take one of the rectangle is this, other rectangle I will take this, one of the rectangle I may take this, another rectangle I may take here this one, another rectangle I may take here, and another will this. So some of them are lower the curve, some of them are above the curve. Okay, so this is a one way of doing this. Okay, and you sum up these all the area of the rectangle, you know, right? Length into width. Okay, so length is here is f of x1 is the height, so that is function is known. So f of x1 into x1 minus a1. So in this case here f of x2 into x1 minus x2 minus x1 and so on. You can sum up the area of, and that will give you the approximation of the this you can say area under the curve y equals to f of x. But we can't say right now that this approximation is better than other ones. Okay, everyone other whatever other combination you take, this is a better. We can't say. you can still, what you can do is you can still increase one more point here, let's say some x6, so then you will have somewhere here point. So you may, so this is one here and one another is, let's say this one smaller one. So there are infinitely many possibilities now. Okay, so what you are doing here is you are dividing, you are dividing this interval a to b into, let's say, so you have, this is a equals to, let's say, x naught. Okay, and you are dividing into less than x1, less than x2, less than and so on, less than xn equals to b. Okay, so how many, so you are a, so x naught to x1, so they are non-overlapping intervals, union x1 to x2, union x2 to x3, and so on. These are union xn minus 1 to x. So we are subdividing into n sub-intervals. Okay, and in each sub-interval, you are creating one rectangle, and you are performing the sum of the area of this rectangle, and that is going to be the approximation of the area. But as I told, this n is here. So suppose this n plus 1 points you have taken. So somebody also can come up, and what he can do is he can add one more point, extra point in between. Okay, so that will give you the new like a new sum of the rectangle. It may be smaller, it may be larger. Okay, we don't know about it. Okay, so we may say that that is a refinement of the partition, previous partition. So once you have considered this n plus 1 number of points, and if you add one more point here, that is called a refinement of this partition. So this is a partition of the interval into n sub intervals. Okay, if you add one more point here, that is called a refinement of the previous partition. Okay, so now what is the Darboux approach is that we are going to understand. Okay, so here means like in the case of Riemann, he is just, what is he is doing is, he in between a1 and x1, let's take this a1 and x1 interval. What he will do is he will create some tag point that he call as t1, and then what he will do is he will it is f of t1. So what he will do is he will passing through this point, that is going to be called as rectangle. So this t1 can be placed anywhere. It may be nearer to a1, it may be nearer to x1, or it may be midpoint of this. Similarly, t2. Okay, so he is just tag the point, tag one point in between every sub interval, and then he is just making the rectangle. It may be over and it may be above. Okay, so this is the this is the Riemann approach. What Darboux is doing is that he is doing somewhere somewhat different. Okay, right. So let's go like next phase. So what is there is, so just what we have done is divide I equals to AB into n non-overlapping subintervals, which we called as partition of I. Okay, and which we call this I1, I2, In. So Ik, if you want to write, what is Ik? A kth subinterval is xk minus 1 to xk. Okay, and the length of the interval Ik, so which we usually denote by L of Ik, and is going to be xk minus 1, and sometimes it is also denoted by delta xk. Means when we are taking the forward point here, delta xk. Okay, so xk minus previous point. Okay, in forward direction. Okay, right. So this is where x0 equals to a and x0 equals to b. So this is called the partition of the I. Okay, so right. So once we have done this, so next draw the vertical lines at the partition points and construct n rectangles. The sum of the rectangles areas approximates the. So that's what we have just now spoken. Okay, so what happened is like this. Okay, so it is here like if it is only n equals to 5. Okay, means n equals to 5 means you have you have the 6 number of points. Okay, 5 sub intervals means 6 number of points. So x0, x1, x2, x3, x4, x5. Okay, and here is mixing. So some of them are above, some of them are low. Okay, so that you keep in mind. So here he is not identifying any tag point here so far. Okay, so suppose, see here, so what will be the error here? So if you look at this graph, this is the error. Okay, plus this will be the error here, this will be also be the error, and this will also be the error here, and this part also left in, so this also will be the error part. So this is the error in this approximation. Okay, actual area, okay, which is missing, or which is actually, so somewhere it is losing here, somewhere it is gaining, right? So it may cancel for some part, but it may not cancel for other part. So there will be an error. Okay, so suppose n equals to 5 can be increased to n equals to, let's say, 50. Okay, so they are now, so now you can look at the thickness of the, earlier it was very huge somewhere. So they are not placed equidistant. Okay, so try to understand, they are not placed equidistant. So you may place them equidistant as well. Okay, so there is no restriction about it. So increase the number of points, so the thickness of the any rectangle, if you take, that is very small. Okay, smaller than the previous one. Now if you take n equals to 50, okay, that will be even more smaller. And what will it will give you is, if you work closely, okay, with respect to each rectangle, you may reduce the error if you increase the number of points. Okay, so there is a possibility about it. Okay, right. So this is a Riemann's approach. Means Riemann approach, what it will do is he will just draw the tag point. So here, what if you look at here, so what is the tag point is, this is the tag point. One tag point is, by using this, it's creating a rectangle. This is another tag point. Okay, another tag point. These are the tag points. Okay, which he has. Okay, so this is the tag point. This is not. This is the tag point. Okay, and this is the tag point, and so on. Okay, so you can actually find out if you know the graph of the curve. Okay, and if you look into this formation of these vertical lines versus the graph of the curve, okay, and that will generate rectangles after creating the tag. Okay, right. So as I told, that there is no restriction on the tag points. Okay, so what Darbox has done is, he has taken two type of tag points. One tag point is in each interval he is trying to get the maximum. Okay, and another type is he is taking the minimum. Okay, so that will create something. Okay, so means new approach, which is known as Darbox approach. But it is anyway is going to be used the sum of the rectangle, area of the rectangle, as the area of the under the curve of the given function f. So it is also going to be equivalent to the Riemann one. Okay, so that's we are going to try to understand now. Okay, so, yeah.
Sir, I can't understand that take point, which is take point and which is not take point.
So tag point is here. If I want to see, this is here, let's say this is x1, this is x2, this is x3, and so on. Okay, so in between this interval a to x1, so I want to create a rectangle. So this is your f of a, this is your f of x1. So if you look at this design here, design is given to you, then you can actually locate the tag point. How? Means by using which height you are taking the rectangle. Okay, width, see, this thickness will not change because the length of this will remain unchanged. So x1 minus a, x2 minus x1, x3 minus x2, and so on. So this width you cannot change. Okay, what you can do is, here if you look at this design, so this rectangle is created by using this height. Okay, so this will be the tag point for this interval a to x1, which you call as t1. Okay, now look at this interval x2 to, let's say, x2 to x3. Okay, look at this interval. So you can't change this thickness here. What you can do is by using this here. So these are almost all the same here. So you cannot distinguish which one is the tag point. Maybe they are similar. Okay, now if you look at here, this interval here. Let's say this is xk minus 1 and this is xk. Okay, now you see here xk height is this and xk minus 1 height is this and xk height is this. So to create the rectangle between this interval, which point is used here, height is this xk f of xk. So this is going to be the tag point, and so on. Okay, so by using the tag point, you are creating actually the rectangle, new rectangle, which is then you will consider the area of that and put the sum over it. Okay.
Okay, sir. So means when we have to create a rectangle, that means that point is a tag point.
Yes.
Okay,
Okay,
sir.
means which you are for that particular rectangle, which one is the height, means like you can say at which point it is going to be getting a height here. Suppose this, see, if you look at here this rectangle here, so here this will be the tag point here. So this is I can't see here, this is going to be the like this here, so somewhere is above, so this is going to tag point. So this is here is like this is creating, so it is neither, I mean, like if you say somewhere it is like xn minus 2 and this is xn minus 1. Okay, so the tag point is somewhere in between now. Okay, so that is, so there. Okay, so it is not restricted. Okay, now if you collect all the tag points, so any tag point, so any interval, if you take, this is a tk. Okay, so here tag point is tk, so f of tk is the height into the length of the width of the rectangle is xk minus 1. And if you put the sum over it, summation k equals to 1 to n. Okay, that will give you the area, sum of all the rectangle, and that will actually, you are going to be approximate this area, which we are going to denote it by integration a to b f of x dx. Okay.
Okay, sir.
Okay, you got it now. So this is the area here. So that's going to be denoted here. So this xk may be replaced by tk here. Okay, these are the tag points, and delta xk is already denoted by the length of the interval ik, which is xk minus 1. So what it suggests, limit n tends to infinity. If you increase number of points, so the rectangle will be more thinner and thinner, and you are careful about the tag points, then it will certainly goes towards the actual value, means that analytical value of integration a to b f of x dx. So that limiting value will be denoted by integration a to b f of x dx. So when you are saying as n tends to infinity, you are essentially saying that delta xn tends to 0. Okay, the length of the any subinterval is tending very close, means like they are sitting very close to each other. Okay, the length of the each subinterval is tending to 0. So they both are the same thing. So if sometime you will say limit n tends to infinity, this integral, this sum is going to be the integral. Sometime you will say limit delta xn tends to 0, and this summation will give you also the integral. Both are the same thing, because as n tends to infinity, if you increase the number of points, obviously the length of the subinterval will get as reduced. So they are means kind of, means they are the same thing you can talk about. Okay, right. Okay, so if n tends to infinity such that the bases of all rectangles tend to 0. Basis means you have the basis of rectangles is delta x n or xk. Okay, so tend to 0, then the area of the staircase figure. So this is, see, if you look at back here, so some staircase with sometime up and down and so on. So staircase is there. So figure tends to the area that is going to be. Yes. So here it's, you look at this limit n tends to infinity. So far we have not said that we have not mentioned that they are equidistant. So if they are equidistant place, so the maximum will disappear. Okay, because delta xk will remain same for every. Okay, so now, if they are not equidistant, then you can take the maximum length, and if that is length, if that is going to be tends to 0 as n tends to infinity. Okay, right. So that will give you the limiting case, will give you the area, and which you are going to denote it by integration a to b f of x dx. Okay, so you wish to identify the area of y equals to x square with a equals to 0 and b, you can say, arbitrarily chosen. Okay, so you have the example now. So you have the let's deal with this example. So y equals to x square is and you have the parabola, right? Sorry, this is somewhere like this. And you want to integrate between the a equals to 0 to some a equals to b. So you have, this is here, somewhere like say, let's say this is b here. Okay, my drawing is not so good. Okay, right. So this is a y equals to x square curve. Now you can subdivide into this. Okay, so you can take delta. So since there is no restriction, so you can take equidistant points. So I can go with the delta x k is equals to, you have b minus 0 by n. Okay. So b by n you can say. Okay, and you can again the tag point at the left hand point of the interval. Okay, so you can say tk is going to be the left hand of end point of the interval. So you have this what is the partition is x naught equals to 0, x1 is equals to, you have this is b by n. Okay, x2 is equals to 2b by n, and so on. Okay, so you have the length of the interval is b by n, and tk is nothing but the left hand point of the interval or right hand point of the interval, that is up to you. So you can say delta is the right hand point of the interval, let's say. Okay, let's let tag point is this one. So what will be the approximation? A is going to be summation k equals to 1 to n f of tk time xk minus xk xk, the length of the interval, xk minus 1. Yeah, xk minus 1. So that is going to be, so xk minus 1 are the same as b by n, and which is independent of k. So you can take b by n out. And another thing is summation k equals to 1 to n. F of tk is what? F of xk, and f of x is what? X square. So this is going to be xk square. So what is xk? Is k times b by n. So this is going to be b by n times summation k equals to 1 to n. So you have k square, b square by n square. So you have, this is going to be b cube by n cube times summation k square, k equals to 1 to n. So this is square term, 1 square plus 2 square plus 3 square plus and so on plus n square, and you know what is the sum of this square term, n into n plus 1 into 2n plus 1 by 6. Okay, so what it happens is this, now this implies, so this implies that area is approximately is b cube by n cube time n into n plus 1 into 2n plus 1 by 6. I'm just using that formula now. Now, what is the area is A is equals to limit n tends to infinity or maximum of delta x. So limit n tends to infinity of this. So that's going to be, so b cube by 6 is out. And you have, this is, you can actually estimate the limit is, this is if you go with the 1 plus 1 by n time 2 plus 1 by n. One of the n is cancelled here and n square here, and 2n are adjusted here. Now, since this sequence is converges to 1, this other sequence is converges to 2. So product of these two sequences also converges to 1 into 2. Okay, so that is going to be b cube by 3. And now if you compare with analytically, that is going to be 0 to b x square dx, and that is going to be x cube by 3. Put upper limit minus lower limit, that is going to be b cube. And it's matching exactly the same. Okay, right. So now, yeah.
Sir, how xk is equal to b square into k square by n square?
See, this is what is f of xk. What is f of xk is xk square.
Xk square.
Okay,
Yes,
right.
yes, sir.
Now see here, if you see x naught is 0, x1 is 0 plus h. So what is the length is b by n. So
B by n.
b, so one more b by n, one ahead with 1 time b by n. x2 is 2 time b by n, 2 step ahead with the b by n. So xk means k step ahead time b by n. So this is going to be xk is equals to kb by n whole
Okay,
square.
sir. Okay.
Is that clear? See,
Yes.
otherwise, first you take one sub interval, then you take 2 sub interval, then you take 3 sub interval, then you take 4 sub interval, and so on.
Sir,
Okay.
will that give the same answer as that analytical method if we change xk?
Yes, it should be. If you take, see, instead of xk, I have see if you change tk, so that tag point is going to be changed. So if you take the tk is the midpoint of the interval also, then also you will get the same answer.
Okay.
Okay, that you can try actually. Okay, if you can take left hand point of the interval, then also it will give you the same answer in the limiting case. I'm talking about the limiting case. I'm not talking about the and this one, the summation one. I'm talking about the limiting. When you apply the limit, so you may get the somewhere expression like somewhere function of n here, and you will get a sequence of n which is going to be converged as n tends to infinity, and that should converge to b cube by 3. Definitely it will going to be. Okay, so you can work with you can choose, so you can have the work like exercise for this. You can choose a tk as midpoint of the interval xk plus xk minus 1 by 2, and another is you can go with the tk as you can choose xk minus 1 of the I answer. Okay, or any other point means maybe nearer to xk or nearer to xk minus 1. All of this, whatever you take it, and you take it in the point in the interval xk to xk minus 1 to xk, that will also converge to the same thing, b cube by 3. Okay, right. So now let's try to understand now Darbox approach, what it is
Sir?
improved.
I can't understand the step of n cube, that how third n is going there. I can't understand n
And cube,
means
because this
first
is,
n.
see here, wait, let's see. See, this is b by n here already outside.
मीन्स मुझे ये वो समझ में आ गया, पर
हाँ.
वो आपने वो उसके बाद स्टेप में जैसे उसको वो सेकंड स्टेप, हाँ उसके बाद मुझे समझ में नहीं आएगा. एक एन तो ऊपर उठ, लेकिन सेकंड एन कहाँ गया वो समझ में नहीं.
Okay, let's I'm just writing. This is equals to b cube by b cube by 6 times Can I write this? This is going to be n, and this is going to be 1n square is going to be cancelled. Okay. Now this n plus 1 by n. So I take 1n with n plus 1, 1n with 2n plus 1. So n plus 1 by n into 2n plus 1 by n.
Okay, sir.
Okay. So that will lead to the 1 plus 1 by n and 2 plus 1. Okay.
Yes. Sorry, sir.
Okay. So fine. It's sometime when the pace is fast, we lose somewhere. Okay.
Yes, addition. So
Okay. So let's come back to our business now. Okay. So the Riemann integral box approach. Now let's try to understand. So let's already understand what is the meaning of partition. So partition means if A is this is a interval in R, then a partition of I is a finitely ordered set. So what is meaning of ordered set means they are in order, means increasing order. We are having increasing order x naught less than x1 less than x2 and so on less. If they are not other than that means you cannot write xn minus 1 here and xn that there that side. Okay, that's a very first thing. So set P of points in I such that this happens. Okay, so points of P are used to divide into non-overlapping subintervals I, and you denote this delta xi by the length of the subinterval I. Okay. Now, okay. Now, what is here we are going to use, because see, we are going to work with a finite sum, and then we are going to take the limiting value. Okay, and we are going to work with the tag points. So let's first try to have the assumption that f is a bounded function. Okay, so f is a bounded function on I. It may be continuous, it may be discontinuous, we don't know. Okay, so let f be a bounded function on I close interval A. Okay, and let this be a P be a partition of I. Now, so since f is bounded on I, means its infimum will exist and its supremum will also exist. Means you take the range f of x such that x belongs to I. Its both infimum will exist. You let's say this is small m, and that capital M is the supremum of this set f of x such that x belongs to it. Why? Because f be a bounded function means what? Means there exists a capital M greater than 0 such that mod of f of x is less than or equals to m for all x in closed interval AB. That's what it means. So it always have infimum as well as supremum. So infimum we denote it by small m, and supremum we will denote it by capital M. Okay. Now, since P is a partition, so you have divided I into n overlapping subintervals ik. K is equals to 1 to n. Now, since infimum exists over the interval I, and these ik's are the sub part of the interval I. So infimum also exists over the interval ik, and supremum also exists over the interval ik. So this gives you meaning about these numbers, that you see whenever you are identifying the thing, so mathematically it should be having some existence. Okay, so whether this always exists or not, that's a very first thing. Okay, so infimum of f of x such that x belongs to ik will always exist because f is bounded. On ik is a subset of I. Similarly, capital Mk will also exist, which is going to be supremum over. Okay, so as already told to you, so let's say let's go one page, then we will come back to here. So here, if I'm drawing the graph here, so let me have this graph here. So this is your A, and let's say this is your B. Okay, and this is your x naught, this is your xn, this is your xn minus 1. Somewhere here is xk minus 1, xk, this is your xk plus 1. These are some points. Okay, right. Okay, so now draw the vertical line passing okay, parallel to x-axis at xk, xk minus 1 and xk plus 1. Okay, right. So where is we will just try to identify the, so this is the interval is ik and this interval is ik plus 1, right? So this is the interval ik plus 1. Okay, now we will try to identify small mk plus 1 and capital mk and capital mk plus 1. Okay, right. So small mk and small mk plus 1 we try to identify. So small mk. So small mk, if you go back and check, mk is nothing but the infimum of f of x such that x belongs to ik. So infimum of this interval xk minus 1 to xk. If you look at this graph, this is increasing over this. So what will be the mk here? This will be the small mk. Okay, and similarly for this is small mk plus 1. Okay, and what it will do is it create a rectangle which is going to be this. Okay, if you are, because you are taking that this tag point here, so xk minus 1 and xk. Okay, and what will be the area is mk into delta xk. And if you take, so what it is doing, so small mk's are doing what? These are, so if you go with mk minus 1 here, okay, infimum, so that always create a rectangle which lies below the curve. Okay, so if you let's say here is let me do one, oh, sorry, let me do some, here is somewhere here, let's say I just change the shape of the curve and we are decreasing as well. Okay, so let's try to understand. So if you look at here, so what is small mn? Mn is going to be this at the right end point of the interval. Okay, and this is going to be when it is decreasing here. So see, this is in this here decreasing. Okay, still it is going to be create the lower rectangle. Okay, low means rectangle lies below the curve. So if you take the sum, so this is mk into delta xk will give you the area of the all possible lower rectangle which are lies below the curve. So if you take the sum over it, summation k equals to 1 to n, that we will call as lower sum. Okay, lower sum which actually depends on f and also the partition p. So that is why this is known as L of f of p. F comma p is the notation because f is function and p is the corresponding partition. So for the corresponding partition, you will have a sum. So if you change this partition, it will be different. Okay. Now similarly, if you try to identify the capital MK. Okay. So capital MK is the, if you recall, what is capital MK is the supremum of f of x such that x belongs to ik. So in this interval, which is the supremum, this is the supremum. So here this is capital MK, which was MK plus 1. For this case, so it is going to be, we give you this rectangle. Similarly, for this interval xk to xk plus 1, this is going to be the capital MK plus 1. And for this interval xn minus 1 to b, This is going to be the MN. So this is going to give you the rectangles. So which are created above the curve Fy equals to f of x. So then if you collect all the possible areas by getting this MKs, capital MKs and delta xk, and you take the sum of, this is going to give you the sum of all upper rectangles, you can say. So that is going to denote it by UFP, which is also known as upper Riemann sum, and this is known as lower Riemann sum. Okay, so in case when both are equal, then you can say it actually approximates the, it will give you the better approximation, right? In limiting sense, if they both are same in the limiting sense, then you can actually say both are equal. Okay, in the limiting sense, if they both are same, then you can say that they actually approximate the area. Now, see, another important point is, so if you increase the point, so this is, so is there any question about LFP and UFP? Because you please let me know first.
Sir,
Yeah.
is it necessary that the supremum is always create a rectangle above the curve and
Yeah, it will be, yes. Yes.
and sir infimum का जो m k into delta x के का जो सम है वो कितना एरिया कवर करेगा, आप ग्राफ में दिखा सकते हैं?
Yes, this will cover this. Means like I can suppose because see, I have already only small mk and small mk plus one. I can go with it. Let me do this. So this is a small mk here. This one only. Okay, for this case. Okay, if you go with the small mks, and if you go with the capital mks, this will give you the area here. On if you look at this curve here, xk minus 1 to xk plus 1. So there is a difference. So here is error. This will be the error in upper integral. This will be the, so here it will be the error in the lower integral. Okay, so if you vary over throughout the interval a to b, you will certainly get. So see, that's what the here infimum and supremum. This infimum will give you the lowest height on the particular integral. Okay, and capital MK supremum will give you the largest height here. Okay, so it's obviously it will create an upper end, means it will create a rectangle which lies above the curve.
Okay, sir.
Okay, right.
Sir.
Okay, so is there any other question regarding LFP and UFP?
Sir,
Yeah.
this LSP, this lower Riemann integral and upper integral can never be equal, no? Because
Yes, it can never be equal. Maybe may never be equal. Yes.
okay,
It is
yes,
also possible. So that we are going to also come with the example. If you are aware about Dirichlet function, if you are aware about, which we have also seen in, I think that
tutorial.
tutorial as well, continuity and so it is differentiable somewhere. So it's 1 for rational numbers and 0 for irrational numbers, that you can show that it is not Riemann integral. Because their upper Riemann sum, if you look at it, it is always 1, and lower Riemann sum, it is going to be 0. Whatever, it is irrespective of choosing any partition. Okay, so means the boundedness of the function will become necessary condition, will not be sufficient. Okay, so function be bounded, but it may or may not be Riemann integral. Okay, so in the limiting sense, they may or may not be equal. So for example, you can take the Dirichlet function.
Okay, sir.
Okay, right. So I just want to add 1 or 2 points here, and then we will end wind up. Okay, so if you consider, suppose if you consider one more extra point, okay, in between this, suppose you are going to consider, let me this area. Okay. Okay. So if I consider one more additional point, suppose here. So let's say this is going to be y. Okay. Or some another notation you can take zk. Another point. So if you include one more point, we call that as a refinement. So that we are going to have a new partition. Okay, which is carrying the p only, but it is only adding one more extra point between them, xk to xk plus 1. So it's going to be the refinement of p, the previous partition. So what it will impact on LFP and what it will impact on UFP. So let's talk about LFP first. So now if you look at here, at this here ZK, and if you draw the parallel line here, okay, so in this interval, what will be the lowest height is this one. Okay, so this will be the rectangle. Now, in this interval, this zk to xk plus 1, what will be the lowest? This will be the lowest. This will be the. So, what it is doing is here is, it is, so nowhere else it will change. Only it will change in between this. Okay, so earlier it was this one, right? Now it is also carrying this one extra now. So what it is saying, that it is actually establishing that it is actually covering more. LFP is going to be less than equals to LFQ if Q is a refinement of P. So if Q is a refinement, you just add the 1 point. Now if you add one more point here, let's say one more point here you can add. So you can see that whatever the area will covered between the xk minus 1 xk, now it is covering more. Now if you look at here, so this essentially this is going to be essentially will be covered, and also so now in this interval here into this interval, this also covered here. So this is going to be extra. So if you add more 1 point or more than 1 point, so what it is going to be is LFP is always equals to LFQ. So if you consider the refinement of the partition, it is going to be LFP is less than equals to LFQ. Okay. So what it tells you the behavior of this sum, lower Riemann sum. So if you take, means suppose one added point is Q. Okay. Another point, if you add to Q, it is maybe new refinement. So it is going to be less than equals to that new refinement LF of, let's say this is some capital T, and so on. Okay, so if you increase one more point, it is actually increasing. So lower Riemann sum will perform a increasing sequence. Okay. Similarly, you can also show that upper Riemann sum will perform like a sequence which is monotonically decreasing. Okay, and then we will apply the monotone convergence theorem that the sequence will always converge. So this sequence LFP will also converge and UFP will also converge, because you know that monotone convergence theorem, what it tells you is sequence, monotone sequence is convergent if and only if it is bounded. So if we show that LFP, the sequence is bounded, that converges. If we see that this sequence is bounded, that converges. Okay, so for looking at that, UFP is greater than equals to, so UFP is going to, can be shown that greater than equals to UFQ. So if Q is a refinement of the partition P, for example, let's say here ZK. So here is your capital MK, right? For one here is this is here, and one is this area. So it will left out this when you so let me look at here. Okay. Yes. Okay. So let's try to see. So this is your MK plus 1 earlier. So this was the area covered. Okay, by the upper integral. So let me erase this. So area is Okay. Okay, let me erase this. Okay. Okay. Right. So yeah. So ZK is going to be crossing this here. Okay. Now in this interval, so now earlier we were talking about xk to xk plus 1 and you were having mk plus 1. So you are having this is going to be the rectangle here. Now if you took zk now, okay, so now you have included one more point. What is happening is, so corresponding to this xk to zk, what will be the highest is here is supremum is this one. So this is going to be your mk plus 1 now. So then you will create this here. So let me use this color. Maybe it may be visible now. This will be covered now. This area will be covered in this interval. When you take this is going to be your mk plus 1 for this case. Now look at this zk to xk plus 1 now. So zk to xk plus 1, which one is highest? This one is the highest. So this is your is mk plus 2. Okay, now what will be here is, this is going to be the part. This is going to, so earlier it was full. Now when you include one more point, it is actually showing the error here. So this will be left out here. So it is actually decreasing. So UFP is decreasing sequence. Okay. Then maybe next lecture we are going to show that this sequence, both sequences are going to be bounded. Okay. And then we will show that actually converges. And you know that monotone convergence theorem tells you if the sequence is increasing and it converges, so it converges to supremum. If a decreasing sequence is there and if it is bounded or it is convergent, it is going to be converging to the infimum. Okay, so that we are going to, then we are going to comment on the Riemann integrability of the function. Okay, right. Okay, thank you. If you have any question, you can ask.
Sir, then both the series will converge to same point, no?
For Riemann integrability, means like when you want to say it is Riemann integrable, then it has to. If it is not, if they are not converging to the same point, okay, then then the function is not Riemann integrable.
Okay.
So supremum of the that LFPs, you can say supremum of LFPs may be equals to infimum of UFP or not. We don't know. Okay, so far we don't know. Okay, it depends on the particular function.
Okay.
Okay, yeah.